Good evening. Today is the 27th lecture of the lecture series X-ray crystallography and solid state chemistry. We are in fact discussing for last few lectures only structure of solids. The basic crystallography we have discussed already. This is a type of perovskite which we discussed in the last lecture, that is lecture number 26. And in these slides, we finished our 26th lecture. Now, let's take another example of anion deficient perovskite. We had one, brown millerite. We discussed it in the last lecture, but this one also just pointed few things in the anion deficient perovskite. But now taking another example, lanthanum nickel oxide. So this is also anion deficient perovskite, and we can see the nickel coordination as a mixture of nickel octahedra and N-nickel square planar planes, and which are ordered in such a way that 2 into 2 into supercell relative to perovskite subcell. What we are talking about, we will see that how we designate this using laser notation we have discussed earlier. So we can see that in A and B direction, octahedra and square planars alternate, but in C direction, it's a corner sharing octahedra connected to adjacent square planar units. Let's say that's the octahedra connected to adjacent square planar plane. Okay, so this, and then what we have done, this is the drawing of the structure of lithium nickel oxide, and well, this is how the direction is shown here. And then we also mentioned in this that what is the space group of these compounds. And when I say space group, we have been saying that C, 2 by C, which immediately says that it is a monoclinic system, and the point group is 2 by N. And the space group is number 15. And then we also discussed what is the cell parameter of this structure. If it is monoclinic, we have A 7.8426, B 7.7988, and C 7.4720, and beta 93.8859 degree. This is what we know very well, that there are 4 independent cell parameters, and that's what we are showing here, independent cell parameters. Okay, we also say that when we describe the 3-dimensional structure of any compounds, we mention space group, point group, and other specific condition of it. And then we also say Wyckoff positions of various atoms and show the coordination values. So lanthanum is in 8F position, and their X value, Y value, Z value, and occupancy factor is here. Nickel are having 2 positions. One is 4A, another is 4B, and you see that the positions are 4A is 0, 0, 0, 0.5 occupancy factor, and 0.050 and 0.5 occupancy factor. And similarly, and there are 4 different positions for the oxygen. We mentioned, labeled it as oxygen 1, oxygen 2, oxygen 3, oxygen 4, and they are in 8F Wyckoff position, and the 8F Wyckoff position, and 4E of Wyckoff position, and their positional parameters are given here, and also occupancy factor. This is the complete description of an anion deficient perovskite of lanthanum nickel oxide. It's got the molecular formula, you can write it like this: lanthanum 2, nickel 2, and oxalate 5. Okay, we go to the next slide, and we can see here there are very many different types of perovskite. And I would say that these materials are referred as also inorganic chameleon. That means that it has got very different type of colors, very different type of composition and physical properties, etc. So I would say many different kinds of perovskite related structure. We have materials. So here we have categorized those types. And we are saying that well, in this syllabus, it has been so that only description of perovskite, but not the classification of all perovskites. So this is what I'm taking, and additionally, the classification of showing a bit details of perovskite, and it is. So the detailed one is double perovskite, and its general formula is A2 B prime O6. And then we have another category of perovskite, hybrid organic and inorganic halide perovskites. Of course, another perovskites, and then mixed anion perovskite. We have oxynitrides and oxyfluorides, hexagonal perovskite. So we see that how many different types of perovskite we can think of. Almost every physical property imaginable can be found in these materials, and that's what we take some example of physical properties of different perovskite here. If calcium titanate, we know that it's dielectric. Barium titanate is ferroelectric. Magnesium, lead, magnesium, niobium oxides is relaxer ferroelectric, and lead, zirconium, titanium oxide, piezoelectric, and then barium, lanthanum, titanium oxide, semiconductor, yttrium, barium, copper oxide, superconductor, bronze, specifically sodium bronze here, is mixed conductor of sodium ion and electron, electromic behavior, and then strontium cerium oxide, and then proton conductor. These are also perovskite type of structure. Rare earth transition metal oxides, mixed conductor, oxide ion, and then electron. And then lithium, lanthanum, titanium oxide, lithium ion conductor, cation, and then manganese oxide 3 minus delta, efficient oxidant, giant magnetoresistance property. So you can see that how many different types of perovskite we can have materials. And if anybody is interested, a very good description is given about this perovskite, different types of perovskite in solid state chemistry and its application by Anthony R. West. One can definitely consult this one, and many other material books are there where we can see the different types of perovskite. Okay, we go for the next slide. We are talking another group of compound. Now, that is typically known as spinel structure. Spinel structure and several commercially important magnetic oxides. These are several commercially important magnetic oxides which contain spinel structure. The parent one is, if we talk about, it is magnesium aluminum oxide. Well, how we describe it? As close specking, we can describe it like this: the cubic close spec oxide ion, where magnesium ion and aluminum ion are in tetrahedral and octahedral size respectively. Okay, now I'm talking a little bit about this structure. If we take 1 octant of the spinal structure, 1 octant of the unit cell, and then we can describe, we'll see the diagram here, oxide, iron in the corner, and then we have also octahedral sites, empty octahedral sites, and this closed one is occupied octahedral sites. This is, we do remember, we are talking about 1 octant of the unit cell of the spinal structure. To describe it more clearly, visibly, we have taken this figure here. And the next figure B, it's a second octant, just underneath the octant we are discussing about in A, where we show the tetrahedral sites. Here is the tetrahedral sites, and this is the tetrahedral sites of it. If we talk about one face of the cubic unit cell, then it shows like this. If we draw it in a plain paper. Remember that we are taking 2 axes and one is perpendicular to the plane of the paper. So unit cell, and the base of the subcell is shown in the dashed line. The base. This is the base of the subcell. Here. Okay. Another one thing we should discuss in spinal structure, so that is how many materials, what type of materials and how many types of materials. You see magnetic oxide, but it's not only oxide, we can see also sulfides and halides can have also spinal structure in different cation combination. A few of the examples we are showing in magnesium aluminum oxide, you see the cation oxidation state 2 and 3. If we take magnesium titanium oxide, which is also spinel, here we can see the cation oxidation state 2, 4. And if we take lithium aluminum titanium oxide, which is also spinel structure, and we can see the cation oxidation state 1, 3, and 4. Okay, if we take lithium aluminum oxide, we see that we have 1 and 3 oxidation state. If we go for lithium nickel vanadium oxide, we can see that we have 1, 2, and 5 oxidation state. This is 1 here, 2 is here, and then vanadium is 5 oxidation state. If we take this sodium tungstate, we can see that this is also spinel structure. We can see that it has got 1 and 6 oxidation state. This sodium 1 and then this tungsten is so 6 oxidation state. We can also see few examples of the sulfides here, zinc aluminum sulfides, where you can see oxidation state zinc 2, aluminum is 3. And we can take another example, copper tin sulfides, and then these are also spinel structure, that copper 2, oxidation state 2, and then 4. So in cation combination, there are limited halide spinels. It's okay. This is an halide spinel, lithium, nickel, fluoride structure. And there you can see cation of anion ratio is 3:4. Well, general formula, we talked about general formula. That is a general formula, spinel structure, general formula. If we go like this, A, B to 2 types of structure. If we talk about AB, in normal spinel, what happened? That A fills the tetrahedral size, B to which fills the octahedral size, and oxygen occurs. So this is how we, if we be octahedral sites and or this part, we can simplify like rock salt structure with cubic closed spec oxide ions, but with only alternate octahedral sites that filled by B cations. Okay, we have to talk a little bit more about this type of structure. And with this slides, we will finish the structure of spinel structure, and then thereby finish also today's lecture. Okay, we can see that if we take the space group of a spinel structure, it crystallizes in face-centered, and then the space group is FD, diagonal plane, and then bar 3 and mirror plane. The space group number is 2 to 4. Once we say the space group, we can immediately say that it is a cubic crystal system. Immediately you can say that. From the point group will be then M bar 3M. So M bar 3M point group, which shows that it's a cubic crystal cubic crystal system. Okay, so we know that formula unit. We also have a parameter. We used to say that how many formula unit are in the unit cell, the cell contents. So the formula unit is 8. So if we take the formula unit 8 in a unit cell, we see that magnesium 8 atom, aluminium 16 atom, oxygen 32 atoms. The cubic closed spectral oxide, half of the octahedral sites are occupied, and we showed it earlier, and aluminium, bioaluminium, and 1/8 of the tetrahedral sites, both T plus and T minus by magnesium. Okay, so that what is there is one unit cell which is showing of a magnesium aluminium oxide, and this is another we have another direction if we look into it and see that aluminium oxygen octahedra and magnesium oxygen tetrahedra. A tetrahedra is in this channel. In between the channel, the tetrahedras are there. You can see also here this. So a combining factor for some spinel structure is that the cation distribution may vary. And two extreme types of behavior may have been distinguished in normal spinel. If it is normal spinel, then if it is a normal spinel, then we say two extreme types. Then another, what is it? That inverse spinel. So we are now talking about normal spinel. All A cations are in tetrahedral side, all B cations are in octahedral sides. An example is this, we said, this is what is normal spinel. If we now describe spinel, we always say normal spinel and inverse spinel. So what is inverse spinel then? You see that we have some of the B sides are in a tetrahedral B cations, and total A plus some B are in octahedral position. So this is what is spinel, inverse spinel. We go to the next slide and then finish today's lecture. Well, the complete range of intermediate cation distribution is possible. A complete range. In addition to normal and inverse spinels, another complete range. So what parameter we use for saying this range? The parameter is gamma. When we have a gamma value is 0, then we call it as a normal spinel. When it is a gamma value is 1, we call it inverse spinel. And then random spinel, that is complete range on gamma. This example we are showing gamma is 0.67. So that is what is the cation distribution in spinel structure and inverse this gamma parameter influences the site preference of the ions, size of the ions, covalent bonding effects, crystal field stabilization energy. These are the particular properties for which we can say the distribution of the cations, and then we describe it as a inverse spinel or normal spinel or random spinel structure. So here are a few examples of inverse spinel compounds. So that's what we have talked about, and that is the cation type and their oxidation state. And then here we have the cell parameter of these compounds, and all these are normal spinel. You take another one here, magnesium iron oxides, which we describe as inverse spinel. It's a inverse spinel, and then nickel iron oxide, also inverse spinel. There we have some other inverse spinel style. With this description of the structures of inverse spinel and normal spinel and random spinel, we finished today's lecture, and we will be taking few other structures, and probably another 2 or 3 lectures. We complete this syllabus, and hope I can give some of the information to you about X-ray crystallography and solid state chemistry. Thank you for today's hearing, today's attendance, your kind patience. We hope to meet you again in the next lecture. Thank you all.